Happy New Year. By the time this is released for YouTube channel, it may be very well Pongal or Lohiri, etc. Anyway, even if it's belated, okay, I hope you had a very academically profitable year. Okay, right. So this is the 19th session on measure theory. This is the Lebesgue integral session number 2. In the first session, we talked about the measure of a non-negative simple function. Okay, we listed the properties. There are one or two points which I forgot to mention, so I will mention. Then we will go to the definition of Lebesgue integral of a non-negative measurable function, not necessarily simple. Okay. So you notice that one of the things which I note, if S is a simple function, okay, with the Ci, or I do not know, alpha I equal to 1 to n. Remember, by our assumption, we always assume this is a measurable partition. This is on a measure space x b mu. Okay, this is a measurable partition. That means these alphas are all distinct also, naturally. Okay, we are assuming alphas are distinct, and this is a measurable partition. Okay, so then one other thing which I may said was, if E is a measurable set, measurable set, and if my I is I of V, this is a simple function. Because it's a measurable function, it takes values only on 0, 1, therefore it's a simple function. But, okay, yeah, I forgot to say, this is the standard representation. Okay. So, then we said integral of f d mu over x, we define in this case to be summation alpha I mu of I equal to 1 to n. This is for any simple function. So if I take my f to be the indicator function of a measurable set E, then we saw integral f d mu over x was mu of E. Okay. But remember, according to our definition, this is not the standard representation. Okay, the standard representation is going to be 1 times I of E plus 0 times indicator function of x minus E, that is E complement. Right? Therefore, the integral of f d mu according to our definition will be 1 times measure of E plus 0 times measure of E complement. So the reason I want to point this out is we are using our convention in measure theory. Okay, that is 0 times infinity is 0. Okay, it's not indeterminate. We also justify it in measure theoretic reasons why we want to stipulate this condition. So for example, okay, therefore this could very well be infinity. Okay, in that case this will be 0 only. For a typical case is when I take R, Lebesgue measure, set with Lebesgue measure M, my E to be Q, then my F equal to I of E, the simple representation is going to be 1 times I of Q plus 1 times I of Q complement. But we know, therefore this, 0 times. Therefore this is going to be 1 times mu of Q, M of Q plus 0 times M of QC. Okay, this is 0, therefore we know this is 0, plus this is 0, but this is infinity, but then this is still 0. Okay, so pause, review, proceed. So remember, whenever we talk about a simple function, okay, it's always good to talk about standard representation. Therefore, you should not look at only the values which are available, but you should also look at the hidden values. Like here, only the value available, but 0 is a hidden value. Okay, but in practice, what we write is correct. Okay. Second point, we proved that the following thing, if S is a non-negative simple function, these all only non-simple, not only simple, non-negative. Okay, if non-negative simple function, and if En a pairwise disjoint collection, measurable sets, right? Then let E equal to union of En. Then we usually say En increases to E. By definition, E is nothing other than union En. Okay, right. Then what we wanted to do was something interesting. So pairwise disjoint. Sorry, I am very sorry. So then we also define if S is a simple function and if E is a measurable set. This okay. We shall deal with this later. If a measurable set, we define what is meant by the integral of S over the measurable set E. Okay. Integral of S over the measurable set E. I think. Okay, this was by definition is integral of S into IE over X of d. Okay, and this is what we saw. Now what we want to do is we want to define a set function mu of S. Remember, S is non-negative and simple. From where? From the set of sigma algebra of measurable sets to 0 infinity. How do I define? Mu S of E by definition is integral of F over E d mu. Notice that mu S of empty set is 0. Why? Because what is mu S of empty set? Mu S of empty set by definition is integral of empty set, integral of S over the empty set, right? And now suppose my S is a simple thing, alpha I of AI. Okay, what does this mean? This means take the integrator function of this into S. This by definition is integrator function, S into integrator function of this over X. But what is this? This we had already seen. This is nothing other than alpha I and intersection A intersection MT, which is summation alpha intersection MT, which is Z, which is same as integrator function of phi. Therefore, in terms of standard representation, S times I phi is nothing other than 1 times I phi plus 0 times complement of phi. Right? So this is, are you following? Do not get confused. I'm just doing little pedantic things, okay, so that you should feel confident. That allows you to get used to the definition. Okay, that is the reason why I'm doing. Okay. Right, this is the definition. Therefore, integral of S I phi over X, this by definition is 1 times mu of empty set plus 0 times X. But this, whatever it is, this is 0. Therefore, this is 0. Therefore, what you have shown is mu S of empty set is 0. So pause, review, proceed. The next thing we proved, that was the last thing we proved, if En is a pairwise disjoint family, of measurable sets, and let E equal to union En, okay, then what we proved was integral of F is again non-negative simple function over E is nothing other than, if you want d mu, is nothing other than f over En d mu and summation. So in terms of our mu as notation, this means mu s of E is mu s of En and summation. That is in terms of this. Pause, review, proceed. Okay, so this we proved already, so I don't want to go through the proof. This we proved. Okay, but I want to interpret this result in terms of the new notation. Okay, therefore mu s is a function from the class of subsets, measurable subsets, to 0 infinity with what are the properties? Mu s of empty set is 0, and 2, if En is a pairwise disjoint collection, okay, then mu of union En, mu s of union En equal to mu s of En summation over N. So what does this mean? This means mu is itself is a measure. Okay. So this is going to play a very crucial role in all the things. Okay. And most often, I mean, this is not done in the typical standard course, but it's a very, very beautiful pearl. Okay. Fantastic observation. So we are creating a new thing. To make you understand, let us try to look at, okay. As I said, my point is, one has to understand it better rather than work towards some kind of exam purpose. If you understand better, when you read a textbook, you will see it makes more sense. And also you can retain the material much easier. And you can also recreate on your own most often. Okay. So let us look at a very simple example. Suppose again, let us look at R with measurable sets. Okay. Suppose my E is 0, 1. Okay. And my call it J. Okay. Okay. My mu s is, my s is the integrated function of J. Right. Therefore, what does mu s? Do you understand that? So mu s, by definition of any set E in M, is by definition integral of S into integrated function of J over R and dU. I'm just going slow. Please understand so that you will become comfortable. Do you understand this? This is by our definition. Right? Now what does this mean? Mu s, this is sorry. Yeah, that's why it's better to understand the definition. Mu s of E is going to be S into integrated function of G. S is this. So mu s of E is, I have to take del over E of S. And see, I'm going back to definition so that I don't make mistakes. S into I of E over all of X. These are here. D. Is that okay? Yes? Okay. And what is my simple function? My simple function, suppose my E is something like minus 10 to minus 10 to half, then E into, what is this? S into intersection this. Okay. Yeah. This is a simple function. This simple function is I of J into I of E. We know this is nothing other than I of J intersection E. Therefore, this is nothing other than integrating I of J intersection E, which you know is measure of A intersection E. Yeah. More generally, okay, consider X be mu and fix A in B and let my simple function be indicator function of A, right? Then I want to claim mu s is nothing other than mu of A intersection mu s of E is mu of A intersection as we saw here. Okay. So my earnest request is please, okay, verify this. This will make you understand the definition of our mu s, the definition of Lebesgue integral. Okay, what is meant by this? This also you will understand. You will also understand ms of E, all these things. Okay, it's a very simple thing, but please do that. Okay, so in summary, what you have done is, if S is a non-negative simple function and mu s of E by definition is integral of S over E d mu, okay, then mu s is a measure on where? On B. Our context is this one. Okay, right. In particular, since it's a measure, we have shown that if an are all in B and an's in increases, let A equal to union an, then we say an increases to A, and we had already shown for any measure mu of an increases to mu of A, right, for any measure. In particular, mu s of an increases to mu s of A. So let me summarize the whole thing. If S is a non-negative simple function, okay, I define mu s of E to be integral of S over E. This by definition integral of S into I over X d mu. Okay, then if an's are in B and if an increases to A by definition is union an, then mu s of an increases to mu s of A. Okay, we are going to use this, so please understand. This is not very difficult, okay, and just because I tried to write carefully the thing, I missed 1 or 2 points. You should not be intimidated. Just go through it, go back to the definition. I immediately want to write the last one. That's why I made the mistake. So mu s of E is integral of S over E. Then write down the definition of that. That is integral of indicator function of E into S over X. Okay, if you write that, no confusion. Okay, this is a very good exercise. Do that, and very useful too. We are going to use it, if not today, in the next session. Now we are ready to define. So, okay, measure space. Let, okay, yeah, from x to 0 infinity be measurable. Okay, now we want to define what is my integral f d mu over x. That is the Lebesgue integral over x with respect to the measure mu. This is what we want to define. Okay. But before doing this, okay, let us recall few things. Okay, remember in the first three lectures when I was trying to give geometric intuitive ideas behind Lebesgue integral, I defined if f is a function from R to R, Riemann integrable, then we claimed integral A to B, the Riemann integral f of s dx. This is the Riemann integral. Okay, is nothing other than the supremum or LUB of integral of s from A to B, s of x dx, where s is a step function and 0 less than or equal to s less than or equal to f. Okay, this is the first one. Second one we did was, if let us assume I is an indexing set, okay, A is our negative real numbers as I varies over I, then we define integral of AI in I, not integral, the summation integral AI. This we said this is nothing else than LUB of s of f, where f in I is finite, and s of f by definition is summation AI, it's a finite sum I in f. In particular, if I equal to n, then we proved that this is nothing other than standard definition of a and n equal to 1 to infinity. Okay, it's almost a year since I did that. Okay, anyway, so this is what we did. So these are the things which are going to motivate. Let's look at the first one. Okay, suppose now I want to have x be mu and f from x to 0 infinity non-negative measurable. Okay, then how do you think I will define this? What is the analog of step function in our case? It's a simple function. So I define it to be the supremum or LUB of integral of s du mu over x, where s is a simple. S is a simple function, so that 0 less than equal to s less than equal to f. Yeah, right. This is our definition. Do you understand this definition? So how do I define if E is a subset of B, measurable subset? How do you think I will define this? This again is by definition supremum of or LUB of integral s over E d mu. 0 less than equal to s less than equal to f, and s is in s plus. That's it. It's the same definition. Okay. This is over E. Okay. So first understand this. This is exactly the same. Very similar. So we have that. What is the first question I would like to ask? See, if f is any non-negative function, I define, okay, integral of f, Lebesgue integral of f over x with respect to the measure mu by the right hand side as the LUB of integral of s d mu over x, right? Where s is a non-negative simple function, so that 0 less than equal to s less than equal to f. Now suppose my f is already a simple function, I have already, that's also non-negative measurable function, for which I already have a definition of integral. Now there is a second definition. So question is, are they same? Is the okay? Question is, if f equal to a simple function, simple non-negative function of course, okay, because f I am taking always non-negative, okay, then I have integral of f d mu, today's definition, and also in the last session integral is d mu, last session, as per last session. I want to know whether these are equal. You understand this? That is very easy, because What is integral of f d mu according to today's definition? It is the least upper bound of integral of, let me write sigma d mu, where sigma is a simple function less than or equal to s and sigma is a simple function. Is that clear? Right? But remember, sigma and s both are simple, and we proved integral of s d mu, integral of s d mu over x is less than or equal to integral of s d mu. That is a monotonicity. You understand that? Therefore, integral of s d mu is an upper bound for the set, for this set. Right? But and interestingly, integral s d mu also belong to that set from this set. Because it's also a simple function less than or equal to itself. Right? Therefore, it turns out the LUB is nothing other than maximum. Okay? Therefore, LUB of this set is integral s d mu, that is the maximum. Right? Therefore, what you have shown is this LUB is same as this. So please understand. So what you have shown, LUB of integral sigma d mu as 0 less than equal to sigma less than equal to yes, and sigma is non-negative, is equal to integral s d mu. But this, according to our definition, is integral f d mu, today's definition. Okay, that's the first thing. Pause. Review. Yeah, that's the first observation you have to make. Whenever we extend sometime, you have to make sure the original one is correct. Okay, it is retained. Okay, it actually extends. Right. Now, what are the obvious things we can ask for? Like yesterday, two things I can ask for. What are they? The first thing is that if C is a non-negative real number, if f is non-negative measurable function, then C times f is also non-negative measurable. Therefore, I can talk about integral of Cf d mu. So, what do you expect? I would like it to be S times integral of C times integral of f d mu. Right? That's the first observation. Second thing is, if f and g are non-negative measurable functions, f is less than or equal to g, then monotonicity I will expect. Integral of f d mu is less than or equal to integral of g d mu. Both are easy. So we will do that. So properties. Yeah. Before going further, let me ask one question. It just occurred to me just now. Why integral of f d mu is not trivial? Okay, f may not be 0. You understand? You understand that? See, there is at least, how do I know there is at least one simple function which is less than or equal to f? Remember, we already proved if f is non-negative measurable, then there exists a sequence Sn of simple functions such that Sn increases to f, where Sn's are in S plus, right? Therefore, there always exists some simple function S. Okay? Right. And integral of simple function we already computed. Okay? Right? Okay. There is also another thing which we already did, but let's not worry about it at present. So let us look at the properties. So pause. Review. This is easy because the fact we need is from real analysis. Suppose A is a non-empty subset of R and alpha is the least upper bound of A, right? And suppose C is a positive constant, then I have defined C of A to be C times X as X is over A. Then LUB of C A, this is a set, this set is C times LUB of A, which is C times alpha. Okay, that fact is what we are going to do. Okay, how do I do that? Let us see that. First thing is, if I said C is greater than or equal to 0, if C equal to 0, the result is obvious because this will be 0, right? Therefore, integral will be this 0, 0. This will be 0, and this is whatever it is, it's an element of this extended real number system, non-negative number. So that will be again 0. You understand that? Therefore, I assume C is positive. Now let us look at. Notice that. Let us look at the set of simple functions S or S plus, so that 0 less than equal to S less than equal to F, and the set of simple functions sigma in S plus, such that 0 is less than equal to sigma less than equal to C times F. Do you see there is a bijection between them? Yeah, because if S belongs to this, look at my sigma equal to C times S. That's again a simple function, and since it's non-negative, 0 less than equal to S less than equal to F implies 0 less than equal to CS less than equal to CF. You understand? And on the other hand, if you give me sigma, then I can go from this way. Sigma, let me take 1 by C times sigma. That is my S, right? So these two sets are in bijective correspondence. Is okay? Now the next thing I want to look at is, what is my integral of f d mu or C of d mu? This by definition is LUB of integral of sigma d mu, okay, over x, where 0 less than equal to sigma less than equal to CF, where sigma is in S plus. This is our definition, make sure, right? But what I do is, this is not only a bijection, you can see that there is a map, right? Therefore this sigma I can as well assume this is LUB of, okay, CS d mu, where 0 less than equal to S less than equal to F. CS is in S plus, right? But what do I know? I know that Lebesgue integral of simple functions, okay, integral of CS equal to C of integral S, right? Therefore this is LUB of C times integral of S d mu, where 0 less than equal to S less than equal to F, and S belong to S plus. Yeah. Now if the set A is set of all integral S d mu, okay, where S satisfy these conditions, okay, this is C times A. This set is C times A. You understand that? Therefore this is nothing other than C times LUB of integral of S d mu. But this C times integral of F d. Okay, so pause, review, proceed. So again and again you can see one has to be very thorough with LUB, GLB, infimum, supremum, or whatever you want to call it. Okay, that is why I hate all real analysis which do not talk about this and immediately jump into metric spaces, open sets, open bars, etc. And now the second property is monotonicity. This is what we call positive homogeneity. See, whenever a scalar thing, this kind of thing, you say it's homogeneous. Okay, since alpha is positive, that is here C. is positive, then you say positive homogeneous. These are all some jargon. What does it mean? F and G are measurable functions, positive measurable function, so that F is less than equal to G. That means Fx is less than equal to Gx for all x. Right? Then I want to show, we claim integral f d mu over x is less than equal to integral g d mu over x. This is what we want to prove. Okay, this is again easy. Let us look at this collection here to define integral of f d mu over x. What is the collection I have to look at? I have to look at the following subset of R. It is R plus actually. What is that? No, following subset, following set. What is the set? It is integral S d mu where 0 less than equal to S less than equal to F and S is in S plus. Right? Then I have to look at. But notice that whenever 0 less than equal to S less than equal to F, this implies 0 is less than equal to S less than equal to G, because F is less than equal to G. Right? Therefore, this collection, collection of non-negative simple function S plus, so that 0 less than equal to S less than equal to F, this collection is a subset of sigma in S plus, 0 less than equal to sigma less than equal to G. Do you understand this? Right? Therefore, let us look at this collection of numbers, integral of S d mu, where 0 less than equal to S less than equal to F and S is in S plus. And now these are set of simple functions. From that I want to talk about the integrals. The set of sigma d mu 0 less than equal to sigma less than equal to G and sigma in S plus. Right? So what we know, since each S here belong to this, so each of these numbers also lie here. That is, A is a subset of B. So pause, review, proceed. So what is that I get? Now I have a subset of this. These are all in 0 infinity if you want. Okay. Then what is known as LEB of A is less than equal to LEB of B. But LEB of A is nothing other than integral of F d mu. And LEB of G is integral G d mu. Okay. So we have proved. This is a very general result. Very general fact. And when I take A to be this and B to be this, I get the result. Okay. Hence monotonicity is proved. Set of non-negative measurable functions. So these are the two easy properties we have proved. Right? The third property is also easy because of that. Suppose A and B are measurable sets. A is a subset of B. Then I can define integral of F over A, integral of F over B. What do you expect? Sure. Why? What is integral of F over A? It is integral of F times indicator function of A. And the other side, integral of F into indicator function of B. Now A is contained in B, therefore what is the relation between indicator function of A and B? Okay, we will do it. So this is as a corollary. Okay, suppose A, B belong to B and F is non-negative measurable. Okay, then integral of F A will be less than or equal to this with respect to mu. Okay, why? This is by definition integral of f into this d mu over x, and this is integral of f into ib d mu over x, right? Okay, but remember, since a is contained in b, I of a is less than or equal to I of b. Indicator function of a is less than or equal to indicator function of b. Yeah, because whenever x is in a, x is also in b, therefore this will be 1. And suppose I start with any other x not in a, this will be 0, but that x may be in b. Therefore this is always true, right? And since f is non-negative, therefore integral of f into indicator function of a is less than or equal to f into indicator function of b. Therefore by monotonicity of the integral, I get this result. Is that clear? Yeah? Yeah. Okay. So these are the 3 important properties, but notice that one of the most important thing, integration, is always we think of a linear operation. That is integral of f plus g must be equal to integral of f into integral of g, and integral of c times f must be c times integral of f. At least for non-negative case and c negative we have proved it. For non-negative function also, then I would like to prove the following. What is that? F and g are non-negative measurable, then integral of f plus g equals integral of f plus integral of g. Okay, this is non-trivial. Yeah, this is non-trivial. That one, to prove that, we require what is called monotone convergence theorem. Okay, so I do not know, I will not be able to prove that completely. So what I will do is I will state the result, and I will also say a second definition of Lebesgue integral, which would have immediately proved it. Okay, but that's what we are going to use. Okay, so this is not the traditional way in the classroom, but as usual you will have in-depth knowledge of Lebesgue integral. See, for example, let us, okay, again it's a kind of what do you call it, digression. See, if f is Riemann integrable, then I have a sequence of partitions. Okay, if you want take equal, okay, that is each layer of length 1 by n minus 1, etc. Call it Pn. Then we know that my integral of f, this, let us look at, remember the upper sums. Upper sums are actually step functions. It is the indicator functions of the let us say xk plus 1. This is xk x0, this is xn minus 1, or whatever it is. Okay, that xk to xk plus 1, k equal to 0 to n minus 1 into capital Mi, where Mi is the LUB of f on the interval xk to mk, sorry, xk to sk plus 1. This again in the first 3 lectures I had already talked about. And this integral Sn, sorry, integral sigma n, these are all step functions, therefore Riemann integral exists. Okay, in fact we know what the Riemann integral, it's a Riemann integral of sigma n is the upper sum of f with respect to the partition Pn. Okay, and then we know that integral of sigma n increases to integral of f. These are all Riemann integral. Yeah. Now I could have done something similar. Do you remember, if f is, suppose come back to x be mu and f is non-negative measurable, then we know there is a sequence Sn in S plus, so that Sn increases to S, Sn increases to f, right? Therefore, why can't I define integral f d mu over x to be limit of integral of s and d mu. Notice that monotonicity we have proved, therefore integral s and d mu will keep increasing. Therefore the limit will exist in 0 infinity. Right? We define it to be. Yeah. The problem here is well-definedness. Okay. What does it mean? That is, if I have some other sigma n in S plus, so that sigma n also increases to F, okay, then does integral sigma n increase to this, the LUB of or limit of integral Sn. Okay, that is the original definition, whether it is the same. That is, integral sigma n limit is equal to integral sigma. We need to prove this. Right? So all these things are taken care of the so-called monotone convergence theorem. So let be a measure space. Let Fn be a sequence of measurable functions. Assume that Fn increases. That is, for each x, when I say it's increasing sequence, okay, that is Fn is an increasing sequence of functions, okay, not F1 is not a sequence of increasing. Right? It's an increasing sequence of functions, because if it's an increasing function, then my x should have an order. x1 less than or equal to x2 implies fx1 less than or equal to fx2. That's not clear, right? So this, what does this mean then? This means that for all each x and x, and for all n, fn of x is less than or equal to fn plus 1 of x. You understand that? Then the theorem says integral of fn d mu over x, okay, the limit, okay, equal to integral of limit fn d mu over x. Now there are a lot of things which you have to understand. The first thing is, since fn's are increasing, right, that is for each x, fn of x is increasing sequence of non-negative numbers. Therefore, if the LUB of fn of a exists in 0 infinity, that is fn of x does converge. Okay, the limit fn of x exists as an element in 0 infinity. Call it fx. Therefore, I have a function, limit function. I call limit fn to be f. That is limit fn of x. That I call it as f of x. That's how my function f is defined. Now, since fn's are measurable and the limit of sequence of measurable function is measurable, this is measurable. Okay. Therefore, this fellow is f and measure exists and it's non-negative. Therefore, integral of f d mu makes sense. This makes sense. Right? Okay. So, what are the things we should observe? Even though it's called a monotone, this also deals only with increasing sequence. Increasing sequence of functions and not with any monotone function. That is not with decreasing sequence. We will see it later. Okay, it's a kind of misnomer calling it as a monotone, because usually whenever I prove for increasing, So students will think decreasing also similar proof will work. Okay, that's how we had been trained all through an analysis. So many students think that monotone convergence theorem is also true for decreasing sequence. That's not true. Okay, and so notice that this also tells about limiting operation. That is limit of integral f1 dn equal to integral of limit of f1. So the integration limit can be interchanged. Okay. Now what is the use of this? We will again talk about it tomorrow in the next session. But what is the use of that? Now suppose Sn increases to f and sigma n also increases to f, where Sn and sigma n are simple functions, right? By this theorem, then limit of integral Sn should be equal to integral of f, and this also limit integral of sigma n, that should also be integral of f. Since the limit is unique, these two integrals are the same. So this well-definedness will follow. Are you following? Just one more observation, I'll stop. Okay. Therefore, if you want to define integral of f to be limit of integral Sn, now well-definedness is assured. But only through monotone convergence theorem, MCT, monotone, number one. Number two, now suppose f and g are non-negative measurable, right? Let Sn is simple function which increases to f, and sigma n be any sequence of simple function which increases to g. We know they exist, right? It may be anything. We already constructed, but it may be anything. Okay. Then Sn plus sigma n, we know this is again a simple function, and Sn plus sigma n increases to f plus g, right? Therefore, integral of Sn plus sigma n d mu over x should increase to integral of f plus g d mu, right? But what is integral of Sn plus dn? We know that integral of simple functions is non-negative simple functions additive. Therefore, this is nothing other than integral of Sn d mu plus integral of sigma n d mu, right? Therefore, what I know is integral of Sn d mu plus integral of sigma n d mu increases to integral of f plus g d mu. But I know this actually increases to integral of f. This increases to integral of g, right? So integral of Sn d mu increases to integral of f. Integral of sigma n d mu increases to integral of g. Therefore, integral of Sn d mu plus integral of sigma n d mu. Okay, the limit of this increases to integral of f plus integral of g. I don't want to write d mu, okay? But this fellow I know is integral of Sn plus sigma n d mu. And I know this fellow increases to integral of f plus g. Right? But the uniqueness of the limit says these two are equal. Therefore, I have proved additivity of the integral. You see that we need if you have established monotone convergence theorem, then only we can prove additivity of the Lebesgue integral on non-negative measurable functions. Is that clear? We cannot directly prove that. And second thing is, okay, that we don't go back to the definition of f plus g, etc. Or look at all the simple measurable functions tau, so that 0 less than equal to tau less than equal to f plus g. We are not using that. Now we are using another definition of integral of f. These are the subtle points. Again, I will explain in the next session. Okay, these are all very beautiful things. Okay, but if you just try to work only towards exam purpose, you will miss all this one. But if you do this, even exams will become easy. You won't get confused. Okay, I hope you enjoy. Stay tuned. We will meet again.